video, we'll be looking at the nucleophilic substitution mechanism for the reaction between halogenoalkanes and ammonia. The conditions being ethanolic, as ethanol is an excellent solvent for both the halogenoalkane and ammonia. Remember, water is not miscible with halogenoalkanes. Halogenoalkanes do not dissolve in water, they're not able to hydrogen bond. Furthermore, any water molecules that would be present would also react as nucleophiles because water molecules are nucleophiles too. Our products are the amine and an ammonium halide. For our mechanism, I should get a pen that works. The halogenoalkane is susceptible to nucleophilic attack because the highly electronegative or more electronegative halogen atom pulls the pair of electrons or attracts the pair of electrons in the covalent bond towards itself, forming a polar bond. The halogen atom is delta negative, the carbon atom it's bonded to is delta positive. Our nucleophile, which is our species that contains a lone pair of electrons in order to form that covalent bond datively, and a partial or full negative charge will be attracted to the delta positive carbon. In this case, we have ammonia. Now, the ammonia molecule, the nitrogen atom has a lone pair. It's also delta negative. You can add that if you wish, and the hydrogens are delta positive. They are less relevant dipoles, really. The pair of electrons on the nitrogen atom are going to form a bond to the carbon of the halogenoalkane. So this curly arrow shows those two electrons, the lone pair, are going to form a bond to that carbon of the halogenoalkane. The pair of electrons from the carbon-halogen bond are going to move onto the halogen atom. Following those arrows through, we have now got, and I'm going to draw my nitrogen and its bonded hydrogens out in full this time because I'm going to be needing these bonds shortly. That nitrogen is now covalently bonded to the carbon, which still has whatever the other three things it was bonded to it, and a halide ion, you can draw the lone pair if you wish, has been kicked out. Now if you notice here, we've got some inconsistencies. My two reactants, the halogenoalkane and ammonia, are neutral. All of a sudden, over here, I've produced a halide that's negatively charged. My charges are not balanced. The other factor to notice is that this nitrogen atom now has 4 covalent bonds. Nitrogen normally will make 3 covalent bonds. It has provided both of the electrons from its lone pair to the carbon to make this dative covalent bond there. Normally, when you're drawing the covalent structure for a substance, you would draw a dative covalent bond with an arrowhead. In the mechanism, we don't bother. That's a slight inconsistency of chemistry, but never mind. This nitrogen atom is positively charged. It has used more of its electrons making bonds, you could say. Or you could even say that it's been protonated because it has 1 extra proton. So we need to have a positive charge on our nitrogen atom. Now this is not the end of the story. This is where our second ammonia molecule will come in. As you know, ammonia has a lone pair of electrons, so can react as a nucleophile. Hello, nucleophile. Ammonia is also a base, because you know that bases are proton acceptors, or they accept protons, they react with H+. So the second ammonia has a lone pair. It is going to accept one of the protons. It's going to deprotonate this ammonium ion over here. it will take one of the hydrogens, I've gone for the one that's closest, and the 2 electrons in the nitrogen-hydrogen bond will go onto the nitrogen. It's quite hard to draw sharp curly arrows with a Sharpie. Following those arrows through, the nitrogen is now still bonded to 2 of the hydrogens. This hydrogen is now part of an ammonium ion, and so I have produced my amine, and I also have my ammonium halide that has been produced. This is a primary amine because there is only one carbon substituted onto the nitrogen atom. You have to have excess ammonia present in this reaction, because if you only had a small amount, if you had excess halogenoalkane, the amine is also a nucleophile because it also has a lone pair. It's actually a stronger nucleophile, which you'll learn about later in life. So it could go on and react with halogenoalkanes if there was excess halogenoalkane. So you want to make sure you have a vast excess of ammonia to limit further substitutions. If I do one example, don't think I've got enough space there. So I'll do one example with chloromethane. Why not? Let's do chloromethane. So here is chloromethane. Here is my ammonia. Ignore that noise, that's a dog barking and my phone ringing at the same time. Pair of electrons from the lone pair of the nitrogen goes to the delta positive carbon of the halogenoalkane. The chlorine is delta negative. That produces the positively charged intermediate with the nitrogen that has 4 bonds, and we've kicked out the chloride. Then a second ammonia is going to come into play and take one of the hydrogen atoms. Pair of electrons from the nitrogen-hydrogen bond goes onto the nitrogen, producing our product, which is our amine. And our amine here, we will name in a second. Hydrogen, hydrogen, hydrogen. And we've also got our ammonium. We therefore have taken chloromethane and reacted it with 2 ammonias, 2 ammonia molecules, to produce our amine and our ammonium chloride. Naming this little amine over here, amines end in amine, the name of an amine ends in amine, so this is methylamine. Or you could also call it aminomethane. We tend to go for the prefix amino when that's the simplest way to name the molecule. If it's a smaller, more simple amine, we tend to go for methylamine. Both would be acceptable at A level.